Alright, hello and welcome. I'm going to show you how I'm using the SASEBO-GII along with some other features of the ChipWhisperer for doing a few tests. So I have the SASEBO-GII board set up here, and the setup I have is there's the normal power measurement shunt, and that's this SMA cable here connects through. I also have a SMA cable that's the 24 megahertz clock coming from the control FPGA. On the Vertex 5, the crypto FPGA, I've programmed it to allow me to input an external clock and to run the AES based on this clock. So this will let me test the effects of different varying frequencies on the AES. And I'm going to use the 24 megahertz clock as a reference to look at how the power signature is changing. So that's that setup there, and I also have this trigger line going into the ChipWhisperer. So if we just do the regular connection, so ChipWhisperer is the scope, SASEBO-GII, hit connect. I've got to change a few things here, so I need to tell the system to output on that target IO out the clock gen module, and I'm going to actually take the sample clock from this 24 megahertz, external 24 megahertz clock, multiplied by 4. It's important to note this 24 megahertz clock is not the AES clock, so this is not the clock you would normally use for sampling. I'm solely doing this because I want to demonstrate how the length of the power signature is changing, just to show you that the speed of the AES itself is being adjusted. So we can capture one, and we have way too many traces here, so let's look at 100 points. So this is the AES running, and the default speed will tell it to measure the clock gen output. So it's running the AES at 60 megahertz. So let's go ahead and change that a bit. So there you have this multiply divide setup. So you more or less can just play around with the multiply and divide to get whatever frequency you want. So there you go. So multiply by 100, divide by 100 gives us the reference 30 megahertz input. So if I hit play, we can see the width of the AES is changing a bit. If I go to, let's go even slower, let's run the AES at 15 megahertz. And you don't see here, sometimes it times out because we're doing this dynamic clock change here. So I just externally can hit the reset button. Let's try a slightly different frequency. Run it at 20 megahertz. Still getting a timeout. There we go. So there we can see the AES running. So now it's running at 20 megahertz. And to confirm it's working, we use the monitor here, which tells us the expected text and the actual text from the AES system. So the Xilinx tools told me the maximum frequency was 125 megahertz I could run this at. So let's see how close we're getting to that. It's important to note that on this board with the Vertex 5, there's no decoupling capacitors because they were removed for side channel. And we'll also need to make sure we have the voltage for the internal part of the FPGA set correctly. And it's some of these things I'm going to show you that affect our result. So I'm going to increase the frequency 37 megahertz. Let's go all the way up. So back to 60 megahertz, and you can see this power signature over here is becoming shorter as it's taking less cycles to do the AES. That is less cycles relative to the 24 megahertz clock because the AES clock itself is speeding up. So we're up to 100 megahertz here. And we can see the system still working. We have the text out and the expected text. And they still are matching. So we're going to start to see them differ as the system's failing, as it approaches its maximum speed. So let's not go quite to 120 megahertz. 125. So somewhere around 120, 115. We can see here the text out and the expected is occasionally differing. So the system timed out here. Let me just redo that. So we're starting to see failures, and we're seeing timeouts here as well. So that seems to be almost the upper limit, which is below the expected 125 megahertz. But if we look at the core voltage, due to that shunt, we can see the core voltage was actually lower than the 1 volt regulator was supposed to be outputting. So there is an adjustment on that regulator to compensate for this shunt, and we'll take it back up to around 1 volt, and we'll see if they work. So now you can see the text out is matching the expected. So that's pretty interesting, because it's showing you that the core voltage is very important for meeting those timing guidelines. Now here it's failed, and again, this is almost undoubtedly because we're missing a lot of decoupling capacitors. So it's sometimes matching, but sometimes not. And you can keep increasing the frequency here, go up to 150 megahertz, and we will start to see, actually here it's working pretty well. So there may be points that it works, points that it doesn't work. And you can sort of confirm based on the length of this side channel analysis trace that you are in fact using the expected frequency. So if I slow it down a little, it's, here's 150 megahertz, we see it's sort of around 40 points. If I go back to 125 or 120 megahertz, oops, it may have just timed out on me here. Try this again. If you go back to 120 megahertz, you'll see that it slowed down. So the AES, it's completely desynchronized, probably due to that changing clock frequency. It tends to not like changing at that high of frequencies really abruptly. And all you have to do is reopen the project when this happens. Yeah, so it's totally desynchronized the Vertex FPGA from the control FPGA, and then now this program's not working anymore. But this shows you how you can use sort of some of the more interesting features of the ChipWhisperer for looking at side channel on the SASEBO board. And let me go ahead and reopen this. And what I'm going to show you now is, before I was using that 24 megahertz clock, which I said you wouldn't do in real side channel analysis, because that's not a synchronous clock. So let's go ahead and use a synchronous clock and look what happens when we change the frequency. So I'm going to use the clock gen output, and I'm going to output the clock gen to the board. So you have to change these settings. I'm also going to take 100 samples, and with a falling edge trigger. So that should be all correct. Let's say 40. And I'm going to take the clock gen. I'm only going to multiply it by 1. I'm not going to use the times 4. So you won't see maybe the expected pattern in your results here. If I reduce the speed, so let's go ahead. Actually, heck, I'll use the 100. 250 I think worked. 150. There we go. So this, we now have a 20 megahertz clock, and we're sampling. We've got to make sure the ADC clock is present as well. When we're changing all these frequencies sort of dynamically, the system can become unlocked pretty easily. All right. Oops. There we go. So you can't see, there's another window here that's showing me there's a timeout error occurring repeatedly. Let's just adjust the frequency to make it a little faster. So we're back to about 24 megahertz here. There we go. If I multiply this clock gen by 4, you sort of see the expected, up-down bumps of the SASEBO-GII. And you can change those a bit. There is this phase adjustability, so depending where you measure, they'll sort of become more pronounced or not. But anyway, those are the, often when you look at a capture waveform, you see these bumps. There you go. Which you may be expecting to see. Anyway, I'm just going to go back to the clock gen by 1. This doesn't affect the side channel part at all. It solely looks a little different. So what's kind of interesting is now we can look at, okay, well, what happens if I run the system much faster? So if I run the system at 40 megahertz, you can look at how the power consumption is changing, or if I run it at, what's this, 75 megahertz? Again, we can keep going. So this is cool because now you can do, if you want to investigate things like the varying countermeasure, you can look at, well, what is the response of the system in the presence of a varying clock? And the ChipWhisperer helps you script that whole thing because you can generate a new clock frequency, take a measurement, generate a different clock frequency, take a measurement, or take a bunch of measurements under one clock frequency. So this was a bit of a random video here, but I just wanted to show you how we can play around with the clock generation abilities of the ChipWhisperer to do some sort of pretty interesting things. So if you wanted to capture, a whole bunch at 120 megahertz. So at this point, it's not a very reliable system, actually. You can see it occasionally failing, 150 megahertz even. So if you're doing these really high frequencies, you probably want to validate somehow that you're actually getting the expected responses. But anyway, I could say, well, capture 10,000 traces, and I really don't need that many traces. Even 40 would be more than enough. There you go. So it's capturing. So that's the using the clock output of the ChipWhisperer for playing with some, more interesting things on the FPGA, running very high speed AES instead of more standard. At 150 megahertz, also, we're running beyond the official sample rate of the ADC, so you may start to get into some issues here. Like many things, you can actually push it well beyond the specs, but hope you found this somewhat interesting. Thanks for watching.